Welcome to this lecture. This is the second and final lecture on sampling distributions, I should say. Well, there is a part of the sampling distribution with respect to sample correlation that we will discuss later, but more or less we would be covering all the sampling distributions that we require for hypothesis testing through this lecture. And again, in this lecture what we are going to look at is a continuation of what we discussed previously. We are going to look at sampling distributions of difference in sample means, of sample variance, ratios of sample variance, sample proportions, and also difference in sample proportion. Now, all of these are kind of in line with the examples that we discussed in the motivation lecture. And let me also tell you upfront that in this lecture mostly it is a statement of results. Neither we will try to prove anything, nor use many standard results that are available and so on. Maybe for a few we will use some standard results, but we will not attempt to prove anything. And anyway, in a 10-hour course there is not much time to prove anything, and we are not interested in that. We want to quickly get to hypothesis testing. And of course, just to reiterate, it is important to study the sampling distributions for hypothesis testing, because after all the entire test of hypothesis rests on the knowledge of the sampling distribution of the test statistics that we use. In the previous lecture we looked at sampling distribution of mean under different conditions, known variance, unknown variance and so on. Now we look at differences in sample means. Again, I would advise you to go back and relate to the examples that we discussed in the motivation lecture. At least one example involved comparison of means, right, where we were looking at the nylon connector example. So of course this situation arises in many other applications as well. So let us come to the point here. When I have two populations of different means, let us say mu1 and mu2, I would like to know, for example, if indeed they are different or not, and for this purpose we set up a test statistic, and this test statistic has to be commensurate with what I want to test. What I want to test is whether mu1, which is the mean of population 1, and mu2, which is that of population 2, are different from each other or not. So naturally the test statistic involves differences in the estimates of means, and once again, as I said in the previous lecture, we are going to use only the sample mean as an estimator of the mean. However, that should not preclude you from or prevent you from using other estimators. So coming back to the sample mean as an estimator, if x1 bar and x2 bar are sample means computed from samples of the respective populations of sizes n1 and n2 and known variances. So we assume in the beginning a simpler situation where the variances of the populations are known, namely sigma 1 square and sigma 2 square, then this test statistic x1 bar minus x2 bar minus mu 1 minus mu 2 divided by square root of sigma 1 square by n1 plus sigma 2 square by n2 is approximately standard normal if the conditions of the central limit theorem apply. What are the conditions of central limit theorem? Well, the observations have to fall out of an identical and independent distribution, right. Now as usual, we usually talk of the distribution of the standardized one, and Z is also the standardized one. Recall in the previous lecture why we talk of the standardized test statistic. One advantage is we can use a standard distribution. Now what if the variances are not known or the populations are normal and so on. This result that you see in equation 1 is for a general population, that is x1 and x2, that is a population 1 and population 2 can be characterized by any distribution in this result. However, if the populations are characterized by Gaussian distributions, then Z follows an exact standard normal distribution. Suppose I do not know the variances, which is the more realistic case, then what do I do? Well, I adopt the same approach that I adopt in the case of sample mean, that is testing of a single sample mean. We replace the theoretical variances with the respective estimates denoted by S1 square and S2 square. Once again, we have not talked about how to estimate sample, how to estimate variances yet. We will do so shortly. Okay. So, the result is again more or less the same. Again, this is for the large sample case, you should remember. The test statistic that is given in equation 2 is approximately standard normal. The only difference between the test statistic in 1 and 2 is that we have replaced the theoretical variances with their respective estimates. And what we will do next is small look at the small sample case, but under two different situations. Variances are equal and variances are unequal. It is possible that two populations can have same variances. How does it make a difference? Let us look at this. So, now as you must have guessed, like in the sample mean case, when the variance was unknown and when the samples were small, the test statistic followed a t distribution there. Here also the test statistic based on the differences in sample means, of course, the standardized test statistic follows a t distribution with n1 plus n2 minus 2 degrees of freedom. So, you can say, well, we lose 1 degree of freedom when we estimate sample mean from population 1 and another degree of freedom when we are estimating sample mean for another population. So, in total we have 2 degrees of freedom loss. Therefore, the total degrees of freedom that we have when it comes to estimating the variance is n1 plus n2 minus 2. Now, we have assumed the variance to be equal or variances to be equal, and therefore, we construct what is known as a pooled variance. What happens is when the variances are equal, we are exploiting this situation to our advantage. From population 1 we have sample size, we have sample of size n1, from population 2 we have a sample of size n2. More the number of observations to estimate the variance, merrier is the situation. Therefore, we are since we are already given that the variances are equal, we pool the data together to estimate the common variance, and that is the expression given to you in equation 4 for the sample variance, where you can see in the denominator we have n1 plus n2 minus 2, that is nothing but your degrees of freedom. All right. So, this n1 minus 1 and n2 minus 1 we already know. What about S1 square and S2 square? S1 square is a sample variance estimated from the first population, S2 square is a sample variance calculated from the second population, and of course, again I say here we have not yet seen the expression for calculating S1 square and S2 square. We will do so very soon. Just to tell you that we are going at probably slightly rapid pace, because as I said early on in the lecture, we are looking at statement of results more than trying to prove anything. And at some point this may get boring to you, but it is an inevitable devil, you can say, that we have to deal with. Okay. So, what about the small sample size unequal variances case? Again the same story, because it is a small sample size, the test statistic would follow a t distribution, and in this case here again we are looking at a non-Gaussian case, and that is why it is an approximately t distributed. The difference between this and the previous cases, the variances are unequal, therefore, I cannot pool the variance estimates to come up with a common variance, and the calculation is a bit more involved, as you can see, particularly in the calculation of degrees of freedom denoted by n12 minus 2. The n12 calculation is quite complicated compared to the previous case, but we have to live with it, but no worries. I mean, most of the times the computer calculates that for you. Nevertheless, if you have to do it by hand, then you have to use this expression, no other choice. But in the end, what is important is to know also the type of distribution, it is a t distribution, that does not change fortunately. And as usual we have x1 bar minus x2 bar as the estimate of the difference in mean. So, in all of this something should evolve for you, that what we are doing is we first identify the parameter of interest, in this case the difference in means, then identify the test statistic. Between the identifying the parameter and identifying the test statistic, there is an intermediate step which is choosing the statistic or the estimator itself, we can say. The estimator here is x1 bar minus x2 bar for mu1 minus mu2, and the test statistic is what you see in each of this. So, that is the routine that we will see in the remaining examples. Therefore, you should not have any difficulty in terms of understanding the procedure. If any difficulty that you may have, that would be in remembering the distributions, but that is all right. In most of the hypothesis testing exercises, typically we do not have to necessarily remember the sampling distribution. Let us say in an exam I have to remember, I do not have to, I can be actually given that information on a simple sheet, and perhaps we will do that for you in the exam. It is not a difficult thing to do. What is important is to understand the concepts of hypothesis testing, that there is a sampling distribution of the statistic that you are dealing with, and that the entire goodness of the entire hypothesis test relies on the sampling distribution, apart from a few other factors such as sample sizes and variances and so on. Okay. So, with this we kind of close the means case, but there is one more example, I am sorry, there is one more example that is going to come up, and with that we will close the means, and that has got to do with the paired difference of means. In the previous 2 or 3 examples, situations, we had looked at differences in means from 2 different populations, assuming that these 2 populations are kind of independent of each other. But now we are looking at a situation where that is not the case, where the 2 populations are not independent. And when does this situation arise? A standard example that is given is a weight loss program where I am looking at a set of individuals, that is I want to test a weight loss program and I want to test that it has been effective. How would I test that? Well, I look at the average weight before implementing the weight loss program, and then the average weight after implementing the weight loss program. So, what I do is I randomly sample a set of individuals before the weight loss program, take their weights and get an average estimate of the average weight, and then put them through the weight loss program, and then again do the same calculation, take the weights and compute the average weight. So, now obviously these are the same individuals that are going to be screened for testing, right, and there is a high level of dependency, and there better be a dependency, otherwise what is the meaning of a weight loss program? When we conduct tests like this in these kinds of situations, it could be a weight loss program, it could be a training program to see if there is an improvement in the performance of teachers or students and so on. There also you will end up with this paired difference of means case, where these obviously the sample size population, the sample sizes are identical for both populations, because we are looking at the same set of individuals or same set of specimens, you may say. So, there is a one-on-one correspondence and you are looking at a pair, you are looking at a paired difference therefore. In this case the independence assumption is violated and therefore it warrants a separate analysis. So, what is the result here? The first thing is you define this variable d I as x1I minus x2I, that is, think of x1I as the weight of the ith individual before the program and x2I as the weight after the program. So, we are not actually testing, it basically amounts to testing the 0 mean, you can say, for d or di. We are not individually testing for x1 and x2, you can think of it that way. So, now having defined a variable di as x1I minus x2I, we can now more or less think of this as a single sample mean calculation or mean hypothesis testing case, but now in terms of d. So, as we did in the single sample case, that means single population case, where we were testing for means. Here we compute the average mean of the differences. So, that is your D bar, and then we calculate the variance in a way that we would calculate for a single population. So, what we have done is essentially taken two populations, but because they are dependent on each other, they have a strong correlation between them, we have clubbed that into a single population now described in terms of this difference variable di, that is all. Now, the result that is given here is for the small sample case. There is no need to specify the large sample case because we know the t distribution tends to a Gaussian distribution. So, we do not need to state that separately. The rest of the story is the same. Now, the test statistic d minus mu1 minus mu2 by your s over root n follows a t distribution with n minus 1 degrees of freedom, where n is the sample size of the individual population. Here, as we said earlier, both populations have to be of identical, both samples have to be of identical size, and that is your n. Very good. Please keep these distributions handy, and of course, I will also bring up the respective distributions when we take up the 8 examples that we had discussed in the motivation lecture for hypothesis testing, illustrating the hypothesis test, all right. Now, let us move on to the estimation of variance. In all of this, we have seen wherever the variance was unknown, I have to estimate it from the sample. Once again, what is the best estimator for variance? There are many different ways of estimating variance. I could look at sample variance as you see on the screen right now, or I could use range, for example, as an estimator of variance and so on. Again, given many estimators, which estimator do I pick is always the question that has been of interest for several decades in estimation theory and continues to be so. For some situations, there are results that are established, but in general there are a set of criteria, as we discussed in the previous lecture, for choosing an estimator. One criteria is that we want an accurate or an unbiased estimator, and two, that we want an efficient estimator, an estimator which gives me as low error as possible, and thirdly, consistent estimator, which is that as the sample size increases, the estimate converges to the truth. So, these are some of the 3 very important criteria in choosing an estimator, and the sample variance satisfies all of this. It is an accurate estimator, which means it is unbiased. The expectation of S square is nothing but sigma square, of course, under some conditions. And then it is an efficient estimator. It is not the most efficient estimator, but it is fairly efficient. So, it will not give me estimates with large errors. And thirdly, it is a consistent estimator. As n grows large, the variance estimate will converge to the truth. Very good. So, with these points in mind, we will stick to the sample variance as an estimator of the variance, and we will work with those with this estimator only. Now, of course, the question of interest is what is the distribution of this sample variance? Can we derive this theoretically? Yes, we can. If you recall one of the standard results that we discussed yesterday, there was one result where we said when I take random variables, standardized random variables that fall out of a Gaussian distribution and square them and add them up, then the resulting random variable follows a chi-square distribution. If I am adding up n such variables, then the resulting random variable has a chi-square distribution with n degrees of freedom. How does that result apply here? Well, look at the expression for the sample variance. What am I doing there? I am actually adding up squared variables. Of course, there are deviations. Are these deviation variables normally distributed? Well, yes, if you assume that the distributions are falling out of a Gaussian distribution. If they are not, what about it? We will discuss that shortly, but assume that the samples are falling out of a Gaussian distribution, then we know x bar also follows a Gaussian distribution. Difference of 2 Gaussian distributed variables also follows a Gaussian distribution. Therefore, I can apply that result here and come to the conclusion that S square follows a chi-square distribution with here with n minus 1 degrees of freedom. That is the only point that we have to watch out for. Why n minus 1 degrees of freedom? Why not n degrees of freedom? Because the result that we had seen earlier says that the resulting random variable follows a chi-square distribution with n degrees of freedom. But the catch here is that although we are adding n terms here, we do not really have n independent terms, and let me actually explain that to you quickly. Adding up n such terms, and the point of contention is whether all these terms are independent. What this means is, let us look at a linear dependence part. From a linear algebra viewpoint, we say that n variables are linearly independent if you can't find a linear combination that will yield that yields 0, or in other words, if you can express one as a linear combination of the other. Now, if you take xi minus x bar, we know that x bar itself has been computed from xi's, right, which means that there is a result. What this means is there is a relation between xi and x bar. How does that come about? From this we can show that these deviation variables are not completely independent. There is a linear dependence between them. How do we do that? We have n x bar equals sigma xi, right, and I have n such x bars, and straight away I can see that sigma minus x bar is 0. So, which means there is a non-trivial combination of xi minus x bars that gives me 0, which means truly this n deviation quantities are not linearly independent. In simply said, if I know n minus 1 deviation quantities, I can construct the nth one. It does not matter whether it is the last one or it is the first one and so on. So, this is another way of looking at the loss of degrees of freedom, and that also explains why I need an n minus 1 here, although I have n terms, so that I get a biased unbiased estimator. And on your calculators, normally we see Sn minus 1 and also an Sn. This Sn minus 1 is nothing but the positive square root of S square based on n minus 1 in the denominator. Very often you will also see in the literature a 1 over n in place of n minus 1. So, we call as S square subscript n. The rest of the expression looks the same, and the positive square root of this leads to Sn. Clearly, if this is unbiased, this is a biased estimator, because expectation of S square n is n minus 1 over n sigma square, or you can say that this is 1 minus 1 over n sigma square. So, for finite n, this is a biased estimator, and you can see the bias here. However, when n becomes very large, then this 1 over n goes to 0. As a result, it becomes what is known as asymptotically unbiased estimator of variance. And therefore, for large n, whether you use S square n minus 1 or S square n, it should not make so much of a difference, but for small n, let us say 20, 30 and so on, it can make a bit of a difference. In hypothesis testing, typically we work with this because we do not know whether we have large samples or small samples, but if I know for sure that I have large samples, typically the preference is for this. The reason is you can show theoretically that although this has a bias, this is more efficient. S square n, although it is biased, it is more efficient than S square n minus 1, which means it has a lower error than the S square n minus 1. And for large n, typically it does not matter whether you use this or not. So, we prefer to use this. There are other reasons also which are beyond the scope of this course. So, the bottom line is we will use this but there is also this competing estimator, and on your calculators, and on a good calculator, you will see both of this. All right. All right. So now we are convinced that there are n minus 1 degrees of freedom only, although we have n terms in the expression for the sample variance. So under the Gaussian distribution assumption for the observation, we can now say that the sample variance follows a chi-square distribution. Typically we work with standardized statistics. So we say that the n minus 1 times s square by sigma square follows a chi-square distribution with n minus 1 degrees of freedom. Now in the general case, when xi's fall out of some arbitrary distribution, non-Gaussian distribution, what can be said? Well, nothing can be said theoretically about the distribution. Maybe for the large sample case, we can say it follows a Gaussian distribution or something like that. But now you can resort to the Monte Carlo simulation approach and check what kind of distributions S square would have for a non-Gaussian kind of distribution. Again, you can go back here and ask this question in the, through simulations. So let us say I do this, say replicate, say 1000 times. What do we want to replicate? The distribution of the or the calculation of variance. So we use the variance command here, and I leave it to you to check in R whether this variance command uses s square n or s square n minus 1 in R. Okay, we will at the moment not worry about it. Now what do I have to supply? Let us give a non-Gaussian distribution, let us say uniform distribution, and let us take about 20 samples, so that we are looking at a small sample case and standard uniform distributions. All right. So you see it seems to follow a Gaussian distribution. What about even fewer samples? Maybe about 8. So you see slowly it is getting skewed, more or less a chi-square distribution, but perhaps with a different degrees of freedom. So the distribution still seems to be chi-square. Now chi-square distribution has this feature that it is defined only over non-negative values, clearly, because as you can see from the construction of the chi-square variable, it is a sum square. So some squares can only be non-zero, non-negative valued, right. Therefore, always chi-square distributed variables are defined over the interval 0 to infinity. We can go back to the large sample case, and you should expect a Gaussian distribution. So we can take here 200 samples and see what happens. You get a nice Gaussian distribution. Everything in this world seems to be tending to Gaussian, right, at least when it comes to test statistics. So that is a nice thing. At least we know in the large sample case everything tends to the Gaussian one fixed distribution that I can always assume. Good. So now let us get back to the discussion. Although nothing can be said theoretically about the distribution, we have to use simulations to do that. What we can definitely say is that this S square that we have defined here on the screen is always an unbiased estimator. Of course, assuming that the xi's have fallen out of a random sample, they belong to a random sample. That means they are all independent of each other. When xi's are correlated, then it becomes a complicated thing to analyze, and we will not worry about that in this course. The next situation of interest is ratio of variances, and I think we talked about this again, whether in the oxide layer thickness for the semiconductor manufacturing process, we wanted to see if one mixture of gases gave me a lower variance than another mixture of gases. So typically we do not compute differences here, we compute ratios of variances, and this ratio of variances follows an F distribution, again with the standard assumptions in place. We assume that we have taken two random samples, meaning collection of observations of sizes n1 and n2 respectively, and also assume that these samples are falling out of a Gaussian distribution. So you see as compared to the mean, the results available for sample variances and ratio of variances are quite restrictive, whereas the sample mean always seems to follow Gaussian distribution or a T distribution, more or less, depending on whether the sample size is large or small. But when it comes to the variance, we have theoretical results available predominantly only for the Gaussian case. There are of course maybe a few research papers that you can look up depending on your needs, what kind of a distribution this ratio of variances follows when they fall out of a when the samples fall out of a non-Gaussian distribution. We will in this course assume that samples fall out of a Gaussian distribution. This F distribution is characterized by 2 degrees of freedom. Again, let me tell you what degrees of freedom means in statistics. Degrees of freedom means in how many independent ways the variability of the random variable is affected. When it comes to the F variable, because it is a ratio of 2 random variables, S1 square and S2 square, we say that the F distribution is characterized by 2 degrees of freedom, nu1 and nu2, and nu1 is n1 minus 1, nu2 is n2 minus 1. The reason for n1 minus 1 and n2 minus 1 is now obvious from the previous discussion. S1 square has n1 minus 1 degrees of freedom, S2 square has n2 minus 1 degrees of freedom. So, you can expect therefore the F distribution to have n1 minus 1 comma n2 minus 1 degrees of freedom. The analytical expression for the F distribution is quite intimidating. It can actually be really intimidating. However, we do not have to worry about it. Normally, we do not give out the analytical expressions. Either we look up a table in a book, or the more modern way of doing that would be to just use the computer software package like R, where you turn to the RF to generate a randomly sample from an F distribution, or PF to compute the probability of a random variable which has F distribution and so on. So, go ahead and actually generate a probability density function, the probability density function of a random variable that has F degrees of F distribution with some pre-specified numerator and denominator degrees of freedom. Again, this is a result, we will use this result in hypothesis testing. Now, the final thing to be discussed in this lecture is that of the sample proportion. Again, recall the example that we discussed in the motivation lecture. There is a manufacturer of controllers for automobile application, and the manufacturer claims that the proportion of defective items is not more than a particular value, and we want to test that hypothesis. So, what do we do here? Of course, now the random variable that we are looking at is a binomial distributed random variable, because now we are looking at proportions where of success or failure. And once again, you should go back to the definition of a binomial random variable and recap all the conditions under which a random variable follows a binomial distribution. And one of the parameters, the only parameter that characterizes a binomial distribution is the proportion or the probability of success rather, which is denoted by P. So, assume that now I actually take a sample of size n from a population which follows a binomial distribution with probability of success being P. X is the number of observations belonging to the success class. Then P would be x by n. So, what I do is I collect a sample of size n and count the number of successes. So, in the case of defective items, I would randomly sample from a lot and through an experiment or through inspection determine what is non-defective and call that as x. Then the proportion, an estimate of the proportion of success, probability of success is given by x by n naturally, where x is the number of success cases by n, which is the total number of cases that you have in your sample. We call that as p hat, as an estimate of the proportion probability of success. The small p is a true probability of success. We will also make an assumption that the population is fairly large, that is important, and the sample size is also going to satisfy certain conditions given at the bottom of the slide. Now, the result of interest to us is on the sampling distribution of p hat, and the result says that p hat also follows a Gaussian distribution, which is very nice, provided certain conditions are met, and one of the key conditions is that the true probability of success is not too close to 0 or 1. That means your population should not have too many success cases or too few success cases. There should be some reasonable balance between success and failure. In that case, the p hat follows a Gaussian distribution. In fact, I would say that go to your R package and check if this result holds good by means of simulation, again using the same idea, repeat your experiments using replicate and plot a histogram. What about the mean and variance of the Gaussian distribution? The mean is NP. If you recall from the discussion on the statistics that we had, we said that the expected value of a binomially distributed random variable is NP, and the variance is given by NP times 1 minus P, but that is for that case. But here as you can see, X follows a binomial distribution, but P hat therefore also follows a binomial distribution, but it is X by N, and therefore you would have here normal distribution with variance P times 1 minus P over N. So, now we move on to the last item in this lecture, where we discuss the case of a sample proportion, and again you should recall the corresponding example that we used in the motivating lecture, where we were looking at the number of defective controllers in the controller supplied by a manufacturer for automobile applications. And in general, of course, this applies to all those cases where we are looking at the defective, non-defective or success, failure, head and tail in a toss, a coin toss and so on. So, the setting is as follows: we have a population characterized by binomial distribution and the success of probability of success being P, and from which we randomly sample observations of size n. The natural estimator of the proportion of successes, the success number of successes in a sample of size n is denoted by x in this slide, and an estimate of the probability of success is naturally x by n. That is pretty much easy to understand. If I want to know what is the probability of getting a head in the toss of a coin, what do? I repeatedly conduct those trials, the coin toss trials, and count the number of heads in those trials. So, let us say I conduct about 100 trials and I count and I get about, let us say, 55 heads. Then the probability of getting a head in any coin toss in general would be 55 by 100. Of course, that would give you 0.55, and as you conduct more and more trials, that is, as the number of observations increase or the sample size increases, we should expect to the estimate to converge to the truth. So, here an unbiased estimator of the probability of success is P hat given by x by n. Why is it unbiased? It is very easy to see. Expectation of P hat is expectation of x by n, and we know from theory that if x is a binomially distributed random variable, its average is NP. Therefore, expectation of P hat is P. All right. Now, with that estimator, question is what is the sampling distribution of P hat? Under the assumption that the population is fairly large and that the probability of success P remains constant, and a couple of more assumptions, P hat approximately follows a Gaussian distribution with expected value P showing that it is an unbiased estimator, and the variance being P times 1 minus P by n. How do you get this? Well, expectation of P hat is expectation of x by n. So, that anyway is established that the mean of P hat is P, which is the probability of success. Variance of P hat is variance of x by n square. right? And we know once again from the lecture, go back to the lecture on statistics, that variance of a binomially distributed random variable is NP times 1 minus P. Therefore, variance of P hat would be NP times 1 minus P by N square, where you get P, therefore, the variance of P hat to be P times 1 minus P by N. Now, this result is valid for large N. That means, in the coin toss example, you would have conducted many trials, or in the defective controller example, you would have collected enough items, not 5 or 10 items in your random sample lot, and also that the probability of success is neither too low nor too large. That means, in the original population, you should not have too few defective items in terms of proportion, or too large number of defective items or non-defective items as well. And there is a typical guideline that is given here, that is approximation is valid when NP is greater than 5 and the other condition that is given as well. So, we assume that more or less these conditions hold good, at least in this course. For the general case, I urge you to refer to the literature. Now, as usual, we work with standard or standardized statistics. Since P hat follows a Gaussian distribution, the variable Z, which is P hat minus P by its sigma, should also follow a standard normal distribution, and that is what your equation tells you here, that P hat minus P by square root of the variance of P hat follows an approximately standard normal distribution, because P hat itself follows an approximate Gaussian distribution. We use this in the hypothesis testing of the proportions. Now, the next lecture, of course, now will focus on hypothesis testing, but before I conclude in this lecture, I would like to reiterate that it is not just important to know these results, but what is equally important is to know the assumptions under which we have derived this sampling distribution, because when you have a case of hypothesis testing, you should first look at the assumptions and see whether those assumptions actually match with the assumptions that we have made here. If not, then you may have to turn to the literature or some other textbook to see what test statistic is appropriate and what is the sampling distribution of the test statistic under the assumptions in which you are going to conduct the hypothesis test. In this course, on the remainder of this course, we will assume that whatever assumptions we have made here are the assumptions under that will apply to the hypothesis test, that examples that we are going to look at. So, the final thing that is of interest to us is the differences in proportions, and again the story is the same, pretty much similar to the difference in the sample means case. We have two different populations. Remember the soft drink example, we have two campuses and we wanted to test if the proportion of students on each campus is the same when it comes to preference for a soft drink. So, here you have two populations from which I have randomly drawn samples of sizes n1 and n2, and as usual all the other assumptions holding good, I estimate the proportions as P1 hat and P2 hat, and the difference, that is P1 hat minus P2 hat, approximately follows a normal distribution, as a result of which Z, which is a standardized statistic corresponding to difference in proportions, also follows a approximately standard Gaussian distribution. Now, Z is not truly a statistic because P is unknown in the denominator, we do not know P. So, what we do is, as far as the denominator is concerned, anyway P1 minus P2 is something that we will postulate in a hypothesis test. So, in the numerator it is not of a concern, the denominator it is a concern. Why have the P1 and P2 appeared in the denominator? Because they are, if you can see, P1 times 1 minus P1 over N1 is nothing but the sigma square, the variance or the, you can say variance of P1 hat, and likewise the other term being variance of P2 hat. They have appeared there because we are standardizing the P1 hat minus P2 hat. So, the point is now I need to know the denominator to be able to calculate the observed statistic. P1 minus P2 is specified by the user in a hypothesis test, but the denominator has to be supplied as well. If the denominator is not supplied, typically that is the case, then what you do is you use the same approach that you use in the sample mean case. When we did not know the variance, we used the estimates of variance. Here the variance is in terms of proportions, so we use the respective estimates of proportions in these terms to arrive at the estimates of the respective variances. So, that is the approach that is used here. At this point, do not get confused that if I know P1 and P2, that means if I am supplying P1 and P2 in the denominator, then where is the question of hypothesis testing? We are not supplying the true P1 and true P2. We are saying I do not know the true P1 and P2. One option is to say I will not solve this problem and go home and sleep happily. The other option is to be practical and say, well, let me get an estimate, and one of the easy ways of doing that is to use the estimates of the proportions from the respective samples and plug that into the expression for Z, calculate the observed statistic. P1 hat and P2 hat are calculated from the respective samples. P1 minus P2 is specified by the user in the hypothesis test, and the denominator is again calculated based on your estimates, that is P1 hat and P2 hat. So, that is the story. Again, you should remember that this result is only valid under certain assumptions, alright. And that brings us to the end of this lecture, in fact the end of the topic of sampling distributions as far as the univariate case is concerned. For the bivariate case, when we look at correlation, we will talk about the sampling distribution of correlation in that respective lecture, that is the respective lecture on hypothesis testing of correlations. The sampling distributions are useful in many different ways, but the two uses for us in this course is in hypothesis testing, and two is in construction of confidence intervals that we will demonstrate later on. So, the next lecture that is in order is obviously hypothesis testing, the crux of this course, where we will introduce some key terminology, type 1 error, type 2 error, p-value, significance level, power of a hypothesis test and so on, and then take the sampling distributions, take the 8 examples that we took up in the motivation lecture, quickly go through all those examples, and we now have all the paraphernalia that is required for hypothesis testing. Now, it is just a matter of implementing the standard procedure. Therefore, when it comes to using this information on the examples, it is going to be fairly very easy thing and a breezy thing, alright. So, see you in the next lecture. Hopefully, you are enjoying all these lectures. Bye for now.